And we are live.
And all live. So, any questions? Okay. What about now? All right, so the homework quiz is on Monday. The master set is Monday. And for some of you, the lab Monday. There's one more thing that I sort of lumped into chapter 18, and the book doesn't go into it, and that's why I feel like we're okay with still having the homework quiz on Monday. Some of the master set questions might be a little bit tricky at the moment. Gauss's law of electricity. So let's talk about Gauss's law of electricity. For some of you, the apostrophe S after an S is that form, so if you want to write Gauss law of electricity, I'm fine with that too. Some books will do it one way, some books do it another. My understanding is that's optional. Gauss law of electricity. And I'm going to do a pseudo derivation. I don't think I posted the full formal derivation for 152. It's definitely a calculus-based problem. But sometimes I post some of the calculus stuff there just for fun. So I have a point charge of some charge Q and a point P right here. So Q for charge, P for just some point. And now I want to figure out what is the electric field at this point. So we'll make it a distance R away. And assuming Q is positive, my electric field goes that way. And what is the magnitude of my electric field?
K equals Q times B. The charge is Q and P over the R squared.
You got elements of it. Or did I mishear? I heard you say K equals Q times P over R squared.
K times.
Okay, so K times.
The charge of Q and the charge of times the charge of P.
There's no charge of P. P is just some location in space.
Oh.
We're looking for the electric field.
Yes.
Oh.
So the formula.
Isn't that force divided by charge?
Oh, yes, except I want the other one.
KQ over R squared?
That's the one I'm looking for. Yeah, you just went too far. Again. So KQ over R squared, or if we did the actual vector form of it, the electric field at point P is, what would be different?
I was gonna say, would it be negative because he took away the absolute value, but there's nothing in there that's.
Yeah, that's not the absolute value symbol right here, and maybe one of these days I'll go to the double lines on the outside instead of the single lines. But that's just for the magnitude.
So we just need the direction as well.
So how would you represent that?
R hat.
Yeah. So it's basically it's KQ over R squared, R hat. And then the other form of this is, instead of using Coulomb's constant, we do it in terms of the permittivity of free space. So we have a 1 over 4 pi epsilon sub naught Q over R squared, R hat. And I'm assuming I've brought this up before. I got a, I don't know, and look for some look, and maybe. Is that what that hand gesture was back there?
I think you did. Yeah, Monday.
Brooke?
Could you repeat what you said? You said instead of using K, you're using.
Right, so we basically have a constant here that developed by Coulomb. I'm assuming there's more than just honor them. And then it turns out when you get deeper into it, we can express that constant up front in terms of what's known as the permittivity of free space, or permittivity. This epsilon right here, that's an epsilon sub 0. Permittivity.
Is that a pi symbol? Next to the.
That's a 4 pi epsilon sub naught on the denominator.
Could you draw the epsilon symbol a lot bigger? I don't know what it looks like. Oh, okay.
The denominator 4 times pi epsilon sub 0.
Got it, thank you.
Permittivity. Now with the sub 0, so epsilon is permittivity, and then the sub 0 part means of free space. In other words, if I have a perfect vacuum of free space. So absolutely nothing in the, so I have an area of space with absolutely nothing in it. I'm going to ignore the fact that if there's truly nothing in it, that it doesn't exist. But permittivity of free space, so in essence, permittivity tells how a medium will react when it's exposed to an electric field. That's ultimately what it tells us. So if I have a piece of paper and I expose it to an electric field, which we will do at some point, then the molecules inside the paper will react to that electric field, and permittivity is a measure of how they react, how much they react. The more polarized it becomes, the greater the permittivity. Now, the advantage of this format is that if you are not in free space, if you actually have a piece of paper there, then the 0 drops away, and now then it would be 1 over 4 pi epsilon sub paper times q over r squared r hat.
So
Yes.
how would we use this in finding the electric field here? The permittivity.
Well, we're not going to. When I derive Gauss's law of electricity, it's simpler in the end if we're doing it in terms of epsilon sub naught instead of k. That's why I bring this up here. Did that answer?
Yeah.
Or good or well enough at least?
It does. Yeah.
Other questions right now? Brooke?
Well, we need to know how to use that in a calculator.
Epsilon sub naught?
Yeah.
It will show up again and again, and then later on in the semester too. In case you haven't figured out what the value is yet, epsilon sub naught is 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. The units are just the reciprocal of Coulomb's constant units. Remember, Coulomb's constant is 9 times 10 to the 9th, so that times 4 pi will get you 1 over epsilon sub naught. You can work it, convince yourself later that that's true. Now, one little piece of the puzzle just thrown in right there. I'm now going to bring in a different element of a puzzle, and then we'll eventually all join it together. The area vector, which I will cleverly call A with a vector symbol over it. I don't think I brought up area vector in 151. All right, so I saw some head shaking no, and then looks of I have no recollection of it. So suppose I wanted to describe the area of this board, as well as the orientation of it. So the actual area, I can find the length and find the width, multiply, I can get the magnitude of the area, but how would you indicate the direction of the board?
With the area vector?
Oh, yes. And if you were doing this from scratch, how would you just define that area vector?
Would you have to set up a coordinate system? Like essentially you get to decide what the direction would be?
Is the
Oh, just always, the area vector is always in the direction that I say it is.
Okay.
Is that what you're going for?
Sometimes that's the
It is
answer.
slightly more formalized than that. Yes, we can come up with a coordinate system, but that should not change the actual direction of the area vector. Just change how we write it.
Does the area vector or the direction depend on what plane, which way the plane is facing, or?
It does depend upon that. So how would you describe the way the plane is facing?
Which way the normal, well, I call it normal, but, I don't know, because there's two sides of the area. There's the, what we could assume is like the back area, like the board, for example. One, you could say is pointing towards us, but you can also say is pointing back.
Okay, so I did hear you correctly when you mentioned the normal.
Yes, the normal.
Yeah. And so what the powers that be did is they said, all right, to define the direction of the area, you can't really go point up or point sideways, because if you're pointing sideways, why not up? Pointing up, why not sideways? There's no preferred direction this way. But what really would define the fact that this is unique is if you pick a vector perpendicular to it. So if the area vector is pointing up, that means the surface is like this. Now Daniel brought in another option of why not have it point that way? And the mathematician said, sure, why not? So the area vector is perpendicular to the surface. If it's an open surface, if it is an open surface, then two choices for A. So the board would be an open surface. I can get from one side to the other without actually having to pass through the board. If it's a closed surface, so open surface, it's a closed surface. In other words, if I cannot get from one side to the other side without having to pass through the material, so if I have a basketball, I'm ignoring where the needle goes in. If I have a basketball, I cannot get from the inside to the outside without actually passing through the ball. That is a closed surface. If it's a closed surface, the area vector points outwards. They did come down on that one and say you don't have a choice. Area vector we're defining as going out. It's outwards. We can do a quick example here. Called X, Y, and Z. And I hat, J hat, K hat. If you recall, J cross K is I. And so I've got $3 meters by 2 meters. That's supposed to be a rectangle in the XY plane. All those years of art school to be able to draw that. My main art background is the fact that my grandmother was an artist. And my mom could draw. And this is what it's come down to. Their legacy. So if I wanted to say what is the area vector of this surface right here, this finite open surface, well, the area vector, first the magnitude,
It's the two numbers multiplied by each other.
yes,
Yeah.
I was hoping someone would say it, just don't make me say it.
6.
Stop it.
Meters.
Squared.
There we go, as a group we got it.
There we go.
6 square meters, but now we have to define the direction. So what would the direction be?
Could it be positive or negative? J hat or Y hat?
Or K hat.
Wait, this is K?
Yeah, K, I made K go up.
Oh. Oh.
Just trying to mess with your heads.
Okay, I missed that.
Now, if I ask what is it, don't put plus or minus. Pick one. I don't care which one you pick, just pick one.
So the two choices for A, if it's an open surface, are it's positive or it's negative. Is-
If you define yes, whatever one of them would be, a minus in front of the other one would also work.
Okay.
Yeah. So K hat, or put a minus sign in front of all of it. So a little bit of a piece too. If I have a closed surface here, so let's suppose that I've got a sphere. What would be the area vector at this point right here, at point P?
Would it be pointing outward, like in the direction?
It would be.
Okay.
So what would be the direction?
Positive R hat.
Okay, so my area vector here, got an R hat, and the magnitude of the area. So no matter where I am, it's always R hat, so we can get away with this.
Oh, okay, so R hat?
The magnitude.
Oh, the next one.
So what's it, 4/3 pi r squared?
You're mixing in volume and
Oh, okay.
And surface area.
Is it just R?
not just R. 4/3 pi r cubed is the volume. If you've had some calculus, take the derivative with respect to r. I don't know if that helps anyone in here. 4 pi r squared. Sorry to spoil it for you. And that's another little piece that we'll bring in just a moment. Any questions up to here before I bring in the third element, and then we'll combine it? Brooke?
So if the object is a 3D object, will it most likely be a closed surface?
I hesitate to say that, because if I have a glass of water, or just a glass that water would go into, I mean, that's a 3D object, but you could, depending on what you're treating as the surface, if you're treating inside the glass as the surface, or the glass itself as the surface, I guess that would be a closed surface. But if you treat it as a cup with a big hole at the top where you put the liquids in, then it's an open surface.
Why was the 6 meter squared K hat? Or why was it in the K hat direction?
Because the area vector is perpendicular to the surface.
okay.
Because when the surface is there, that means it's up or down.
Gotcha.
And despite what Anna wanted, I made K hat.
Gotcha.
Other questions at the moment? All right. And the third element that we need to hit on beforehand is, suppose there's an electric field going from my right to my left. So just sort of picture a bunch of arrows shooting across. And then I put this piece of paper in between. So imagine that you've got a number of arrows hitting it. Now I turn it like this. What's true about the number of arrows that hit it?
There's less.
Definitely. Or if this is, infinitesimally thin, then none of them theoretically would hit. Unless you're Robin Hood. So we got these arrows going across like that. So I want to somehow describe mathematically the number of arrows that are going to hit this piece of paper based upon the direction that the arrows are going and the direction and the orientation of this. As well as, if this were a bigger piece of paper, more arrows would hit it that way. So somehow area needs to be taken into account, the electric field taken into account, and
The thickness of the paper, is that?
we'll just stick with infinitesimally thin right now.
Okay.
If you want to complicate it,
No, I'm
Okay.
good.
I was going to wait for the test to complicate it. So if we think about that, so this right here, what's the direction of the area vector here? Okay, one or the other. And we're going to say that the number of arrows that appears is close to 0 if this is infinitesimally thin, despite Harrison's desire to add the thickness. If I put it like this, what is the direction of the area vector?
This way or this way?
Yeah, so let's, traditionally, it doesn't, yes, it's this way or that way, absolutely nothing wrong if you want to say the area vector is that way. Traditionally, if there's an electric field going through it and you're doing that analysis, you pick the direction the electric field's going in to be the direction of the area vector, given a choice. However, it is more of tradition and brainwashing than a necessary thing. All right, so I have it like this. So I need to somehow come up with some mathematical operation that's going to, where I take my electric field and my area and somehow combine them for this to not to be 0 and for this to be 0. And what mathematical operation do we have that will do that?
I'm gonna say sine or cosine.
Okay. We can do it from that point of view. So talk to me. How are we going to bring in sine and cosine into this?
Well, I'm thinking about like, I'm trying to think back to some of the other physics classes I've taken to where like, well, torque, for example, is what was in my head. That's why I said that, because, you know, it matters where it's applied and like the direction it's applied.
Okay. What else? Besides torque, what's the other thing that depends upon the direction?
I'm not sure.
I worded it incredibly vaguely, but hopefully. Torque depends upon the relationship between the moment arm and the force. Suppose we're dealing with force and displacement.
Projectile motion?
You don't really bring force into projectile motion problems. I mean, it's implicitly there when you make the acceleration downwards g, little g, or at least the magnitude. But force doesn't really play into that directly. I can see the impact that chapter made on all of you.
Force diagrams. Buzzwords.
Yeah, well, you know, I was thinking work.
Yeah.
So torque, if you recall, R cross F, that definitely brings the orientation into it. And then the other one is work, and the formula for work.
1/2 K mv squared.
I think 1/2 K in.
Wait, never mind.
You're thinking of the formula for kinetic energy? Hey, you know what? Let's impress the people who have This is going to be great. It's going to be a chorus of angels.
Waiting for this moment.
Because I said last semester,